As I said, thank you very much for the introduction. Today, I would like to talk about energy forecasting and especially on how to advance accuracy in energy forecasting using mixture of experts and federated learning. So before I talk about that, maybe we should think about a little bit why we would use energy forecasting in general. So if we look at it on a building level, then we see that we have increasingly installed solar panels that are kind of volatile in their supply. And we also have some demand uncertainty because you kind of never know whether a user will use an appliance or at a specific time. So that's why it's quite challenging to actually manage supply and demand accurately. And here energy forecasts come into play. So some ideas, you could basically use energy forecasts for power dispatching or for intraday generation planning, but also to enable demand response programs. So for example, you would need some idea about how much load is available, how much flexibility inside this load is available. So that would be quite important. And in general, you can use these forecasts as an input to an energy management system in order to reduce energy costs or emissions. So energy forecasts are quite important in some areas. However, before we talk about it in more detail, maybe we should clarify a few things. So when I talk about energy forecasts, I mean photovoltaic forecasts. We see that on the top here. I also mean load forecasts. We see that at the bottom, or presumption forecast. That's when you sum up PV and load together. And when I mean short-term load or energy forecasting, I mean predicting like the next hours or the next day, but yeah, within an hour region. So if we look at short-term energy forecasting, it's quite challenging to be accurate here because the patterns, especially here for load, are quite complex and volatile. So it's challenging to be precise here. And one idea would be to use, for example, different data sets. As maybe if you just install a smart meter to collect your data, then you say, well, I don't have any seasonal patterns already, or I've only been to vacation once. So maybe if I compare this to other buildings or the effect of electric vehicles, it could be a good idea to also include other data sets. However, energy data is quite privacy important because, for example, from the load patterns, you can see whether the person is at home or not, if he's on vacation or not. You can see if the person has an electric vehicle, maybe even which type of an electric vehicle. So maybe you don't want to share this data with everyone. And here federated learning comes into play. Just to give a short overview about federated learning, we go more into detail later on. You have different buildings installed with PV and different appliances. And for each of these buildings, you then have your local forecast models. So for example, you have one forecast model for photovoltaic, one for consumption. And then instead of sharing this data with the different models, you only train or you share the trained model weights with the other person. So you would upload, for example, the weight metrics of this neural network to the server, and then just take the average of both weight matrices, and then the improved weights you can distribute it back to the forecasting model, and that can improve accuracy in theory. So the important thing to take away is the data stays local, but you can still improve by sharing your model. We can see that this works quite good, for example, for vision or the language domain. We can improve data privacy because we don't give our data away. We can also improve network efficiency because we don't have to upload all this data, but only the model weights. And we can actually also improve accuracy. However, with energy data, that's not so much the case because the data is so different that the accuracy often stays the same or even gets worse. And that's why we need some more generalizability here. So the idea was to get a mixture of experts into play. That's basically a kind of model that enables more generalizability. If we look at our basic model architecture, for example, here a long short-term memory model in LSTM, we have an input sequence, and we have different LSTM layers and the output sequence. And you could replace one of these inputs or the LSTM layers with a mixture of expert layers. introducing different submodels. So here, for example, you would have 1, 2, 3 submodels and a gating network, which tells you which of the experts you want to activate. So for each input sequence, you would not use the whole network anymore, but you would activate selected parts of the network that are specialized on, for example, this data sequence, and thus enable the whole network to generalize better. So we want to use this mixture of experts to apply it to federated learning and able to actually improve the accuracy here. And that's the problem we would like to solve. So our main contributions are that we show for a mixture of experts models with different gating mechanisms and a different own loss function. And we show that we can improve the accuracy by up to 9%. And we also introduce different benchmark models, but more to that later. So the first question would be, how does this mixture of experts actually work? If we look at on a more detailed level, we see that we have 2 gating mechanisms. One is soft gating and one is top K gating. So the soft gating would be that we have an input sequence. So maybe the last 24 hours to predict the next value. And then we give this to different experts. And the gating model here calculates the probability which expert might work best for this input sequence. And in soft gating, you would use all these probabilities. So if expert 1 has a probability of 10%, take the 2 10% expert and 80%, then you would weigh this expert with 80% and the other 2 with 10%. But you would use all of them, so all of your model would be activated. With top K gating, you would only select, for example, if with top 2 gating, the top 2 experts, and leave out all the other experts. Or with top 1 gating, you would only consider the expert with the highest probability. So this might seem like a good idea. However, in reality, you often have the problem of dying experts, meaning that at the very beginning, if one expert is very good, the gating network learns to only use this one expert, and therefore it behaves like a normal network because all the other experts remain unused. So we have to introduce some regularization here. As we heard before, we could also use some other forecasting metrics here, but we use RMSE, the root mean squared error. And then we have 3 different penalties, one for expert importance, one for expert outputs, and one for expert weights. What do they mean? Expert importance means how important is each expert compared to the others. So if I have 5 experts and every expert is used 1/5 of the time, that would be perfectly balanced. However, if I use one expert 90% of the time, then this expert would be overused and we would penalize this overusage here with this factor. And then the other 2 penalties would consider that the expert weights should actually be different, because if the experts behave quite in a similar way, we don't need different experts here. We could just use one. So if the matrices here are quite similar, we also penalize that by building the inner product and subtracting the identity matrix. When we have this new loss function, we don't want to penalize it all the time, but only at the beginning and in a decaying way, so that later on, maybe at some points, it's a good idea to have similar experts for some sequences. So this decays over time. Now we want to apply this to federated learning. So this is where the models here come into play. And to even simplify the learning a little bit for the models, we use clustering. So if we have similar buildings, they come to one cluster, and if one building is very different, we put that into a different cluster. And here we use k-means clustering with dynamic time warping as a metric. And given the different forecasting models here, we then provide these weights to the aggregation server. And here we basically, or the most simple idea would be to just build the average over the weights. So if you have 2 matrices here, you would say 1 divided by 2, and then the sum of the weights. And we also clip this value and introduce some noise to emphasize a little bit more exploration. So that's our basic federated learning setup. And now a little bit about the experimental setup. So for the data set, similar to the talk before, we also use the Osco data set. This has like 300 different buildings and quite good documentation. We did also include some weather features. And to include these weather features, we did some feature engineering. I think here it would be more interesting to talk about this later in more detail. But for example, we did Spearman correlation, but yeah, that's too much detail. And then these final features we included to our normal value. So we take the past 24 hours to forecast the next value and additional these features here. Then for our forecasting models, we have 4 mixture of experts model. One time we use the dense model architecture, one time LSTM architecture, and every time we use soft gating and top 2 gating. And then for benchmarking, we tried several different model architectures. So we read different publications that also used the Osco data set to try to implement their models. We used LSTMs, bidirectional LSTMs, convolution neural network, resonant architectures, transformers, and the best 3 architectures here were selected as benchmark models. And then for the training architecture, we used 100 epochs for training, 3 federated learning rounds for training, and 10 clusters. So if you look at our results, I will go over them quite quickly. At the top here, you can see that the forecast for load kind of works. However, I think it's impossible to have a perfect load forecast because on building level, on a single building level, you never know whether a person will use an appliance or not. So there is some randomness within this forecast, but you see that the model can predict the general pattern of the forecast. And the figure at the bottom should indicate that there's quite a difference between the different clusters. However, I will talk mostly about the results on a total level. So if we compare our best benchmark model, in this term, the LSTM model, with our best mixture of expert model, the soft-gated LSTM model, then we could improve the forecasting accuracy by 9%. And if we look at our RMSE of 0.15, compared to presumption forecasting, for example, we see in presumption forecasting a lower RMSE. So here in presumption forecast, we are a little bit more precise, which makes sense because presumption has a clearer pattern, as we see at the top. And in presumption forecasting, for example, we could improve by 9%. I think the details are more easy to discuss later on. But we also look from this 9%, which factor can be attributed to the model architecture and which percentage can be attributed to the federated learning. So we compared how does mixture of expert perform if we train it locally and how does it perform when we train it in a federated learning way. And we see that 2% can be attributed to the federated learning and 7% to the improved model architecture. This is different, for example, for PV forecasting. Here we see an improvement of 6%, but actually nearly 5% can be attributed to the federated learning. I think that also makes sense because the data patterns are way more similar. And if the data patterns are more similar, then also the federated learning, the data from the other buildings is just more useful. So this would also be one important takeaway, that data still needs some similarity. Then only briefly, we could evaluate zero-shot learning. So we took the 42 models for user 1. So 7 models in general, 2 learning architectures, 3 data sets, and used them without any retraining for 30 other users. And here we only compared always the best performing architecture and training. And here we could see that even with unseen data, the mixture of expert was 11% up to 42% better, depending on the data set. Also indicating that mixture of experts can improve generalizability. And then briefly, the training time. The main takeaway here is that, yeah, the training time basically stays the same. It decreases a little bit, but only it's like 16 seconds. I think it's important that we see that the improved accuracy is not on cost of training time, but actually we could also decrease training time. This brings me to my conclusion. The main takeaways here are that mixture of expert is quite interesting, I think, for many forecasting architectures to be included, because it can actually improve accuracy while also reducing variance. So we see that if we repeat the forecast several times, then the variance also goes down, and therefore the forecast is more reliable. The training time also decreases a little bit. So I would recommend to also apply a mixture of experts for your forecasting models. And for future work limitations, we see that we could also test this on different data sets. However, data sets for federated learning are quite rare. So that would also be an interesting research direction. It's always challenging to find good benchmark models because there are hundreds of models out there, and you at some point have to limit yourself to some benchmark models. And in the future, you could also try different federated learning aggregation algorithms or more gating mechanisms. And yeah, one other important aspect would also the security of federated learning, but that would be another topic. So that brings me to my end. Thank you very much. Now I'm open for questions.
Yeah.